Greetings and welcome. We are reviewing for our chapter test on statistics and data analysis. This is specifically problems from pages 934 to 930 something else. And we're taking a look at this. Here's a frequency distribution. Remember that a frequency distribution is a chart essentially telling me how many data values are within certain classes. And here's what they ask. They say, what is the range of the data? Technically, this answer is an approximation because I don't know what the lowest value or the highest value was, but here they're assuming that the lowest value was 9 and the highest value is 14. So for problem 11, they just did 14 minus 9 and got 5. All right, so technically that's an approximation. It's possible that all three of these values were less than 14 and both of these were bigger than 9, and it would be a smaller range than that. But I guess this is the maximum range that we could have. If I was interested in problem 12, like what the class marks were, that's the midpoints of each class. So the class marks, what did we refer to them as? Did we use xi for the class marks? I think. So the marks, so this would be like 9.5, 10.5, 11.5, and so on. For the class marks. And then drawing a histogram. A histogram is a bar graph of a frequency distribution. Let's see if I can quickly throw one together here. So let's see, started at 9, and the class intervals were 1, weren't they? Yeah, so this is relatively small. And I'm just going to override this. So we had 2, 18, 5, 2, 18, 5, and then 2, 3. And let me clear this list for fun. So our histogram would look something like this, except the widths of each bar would be the width of each class, where it would fully fill that out. And you can then see kind of a little bit actually regarding the variability of the data, where I can see that, I mean, it's not a normal distribution. If I was to say have infinitely many classes and infinitely many data points, it would probably look something like this. But you can see that there's a cluster of data between 10 and 11, and then there seems to be, you know, another little peak over here as well. But yeah, that's what a histogram looks like, something like that, except these widths would be the full width. One thing to point out about the class limits is the two data points in here could be equal to 9, but are technically less than 10. So they don't include that, but they do include the 9. So if I had a data point land on 10 exactly, it would fit in this class because that's the one that includes 10. So greater than or equal to 10, less than 11 in that case. All right. So that's worth pointing out. So let's see, let's look at another set of problems here. It says, suppose 150 values in a data set are normally distributed. All right, normally distributed. Here I'm just grabbing my little chart that I'm anticipating having to need. It says how many values are within one standard deviation. Well, within one standard deviation, it sounds like for problem 26, that's an about the mean question. So t is equal to 1 standard deviation above and below. If I look up the p-value for that, one standard deviation above and below is 68.27%. All right, something like that. I could find that on our little chart that we had where I'd look up the t-value, go down to the 1, and then there's my decimal percentage of that value. All right. So if this is the percent of the data within that range, and I have 150 values, and I want to know how many values are between those one standard deviation above and below, it's going to be 68.27% of 150. So I could just take the 0.6827, multiply by 150, and I get 102.405 data values actually landing in between there. I'm assuming they might have used the 68.3 round which is fine. So they rounded to a tenth rather than a hundredth. 27, it says how many values are within 2 standard deviations of the mean. So in this case, t would equal 2. The value of p is going to be larger. So 2 standard deviations lands us right here, 0.9545. So 95.45%. So I would just take 0.9545 and multiply by 150, and that would convert that to values. So 0.9545 multiplied by 150, and I get 143.175. And then it says how many values fall in the interval between the mean and 1 standard deviation above the mean. So let's actually draw a picture of this for 28. Oh, that's a relatively straight line there. I'm kind of proud of that. So here's my bell curve. And they said between the mean, so the mean is occurring right here. And actually what's interesting about this problem is I don't even know what the mean is for this problem. I don't know what a standard deviation is. I just know that it's normally distributed. So there's 1 standard deviation, there's 2 sigmas above the mean. Right, so that's, I guess this is technically x bar plus a sigma, right, x bar plus 2 sigma, and so forth. And they're specifically asking how many lie between the mean, so from this value, and 1 standard deviation above the mean. Now that's actually kind of a nice setup there. It's just going to be half of the number that would lie above and below, or half of this number right there is how you'd end up with that. Now I had a student ask, what happens if it doesn't land exactly 1 standard deviation above? I think I might be able to answer that question with one of the next series. So let's take a look at that. So here's problem 36 through 39. Oh, let's see, is that going to fit that exactly? Maybe not. Let me go back to this, and I'll make up my own problem. So let's say that if x bar was 50, all right, and let's say standard deviation was 5, all right, assuming that's the case, how many values are, let's say, less than, what if I said 57? And now the problem is that 57 doesn't land on one of my standard deviation tick marks, right? 57, right, if this was 50, this would have been 55, this would have been 50 plus 10, which is 60 apparently. 50-10, I'll call it. So 57's landing somewhere here, and I got to figure out what is that in terms of standard deviations above the mean. Well, the way we could find that is if I take 57, subtract the mean from it, all right, and I'm going to do some more work in this just a second, and I get 7 units, okay, this is 7 units above the mean. That's not in standard deviation, that's in units of whatever this is measured in, ages of people, who knows. But I want to divide by the number of units in a standard deviation. So if I divide this by 5, by a sigma, I get 7/5, which is, what's that, 1.4, I believe? Yeah, 6/5 would be 1.2, yeah. So that means 1.4 standard deviations is what I'm looking at here. All right, so 1.4 sigmas above the mean. Now in this case it says how many values are less than 57. That would be a z value I'd be interested in, not a t value. And so if I look at my chart, z value, all right, that's my middle chart there, go down to 1.4, I get 0.9192. So the corresponding p-value, percentage, is 91 point, what did I say, 92%. All right, so if I wanted to find out how many values, I could just multiply 0.9192 times 150, and I get 137.88 values, okay, are less than 57. Okay, so regarding this little formula to find, I guess, standard deviations from mean, my formula is I took, what did I refer to this as? I don't remember what I referred to that as. Well, basically, I'd subtract the mean and divide by sigma. I don't know if you want to call this plain old x, whatever point you're interested in, whatever data value. So if I take the location I'm interested in, measured in units, subtract the mean, and divide by sigma, that's going to give me the number of standard deviations from x bar, all right, which then I could interpret as a t-value or a z-value, whichever I'm interested in at the time. Question?
If it comes out as it needs to be a t-value, do you do anything differently with the t-value?
Well, if I was asking, for instance, in that case, it would have been how many values are between 48 and 57, and that would have been 7 above and 7 below. You know, I could use a t-value perhaps, or maybe I was interested in, you know, between two different values. What if it was like 2 standard deviations below and 1.4 above? I might have to have some sort of, you know, hybrid problem of maybe using a t-value and cutting it in half, and then a t-value and cutting it in half, or something like that. Once I find the percentage, I could. I'd be able to do that. So, like for instance, when they ask the question, how many values fall between the interval of 1 standard deviation above the mean and the mean, I looked up the t-value, which gave me this percentage. All right, but I didn't want the whole thing. I just wanted half of it. So I divided the percentage in half. Whereas if I divided the t-value in half, I would technically have gotten this percentage, all right, which is actually bigger than this percentage, I think. Oh, actually, that's... I'm not sure. Yeah, I think that's going to be bigger. Yeah, definitely. 100% now. Yep, okay. I just had to think about that for a second. So anyway, so that's how you can find the number of standard deviations if it lands on a weird location. Let's see, one last question. It says in a random sample of 200 adults, so n is equal to 200. It was found that the average number of hours per week spent cleaning their homes, x bar, is 1.8, with a standard deviation of 0.5. Meaning, if you spent, say, 2 standard deviations above the mean, all right, which would be 1 whole unit. If you spend 2.8 hours per week cleaning your home, that means you're like cleaning your home more than 95% of the people who clean their homes, right, per week. That's pretty good. You're a clean person. That's what you are. There you go. So here we go. I would actually argue that most of this time spent cleaning your home is probably prior to company showing up, like the last half hour. I bet I would wager. What is the standard error of the mean? That's sigma sub x bar, and that was the standard deviation divided by the square root of n. All right, so square root of 200 is 14.14. Take 0.5, divide by that, and I get standard error of the mean is 0.0354, I'll call it. All right, so there's my sigma sub x bar, standard error of the mean, and that is describing the distribution of where the true mean lies as compared with my sample's mean. Okay, so I'm looking for mu, the true mean, the little Greek letter mu there, right? So let's see, what question were you guys specifically interested in, 37? Or 39? Let's see. I might crank through all of these, I think I have time. Find the range about the mean that such that the probability is 0.9, that the true mean lies within the range. Now, if the probability is 0.9, what is my level of confidence if the probability is 0.9? Then that means, yeah, my LOC is, technically it's a 10% level of confidence, or 0.1, right? So the level of confidence was kind of the 100 minus the percentage of the probability, is right, kind of how we describe the level of confidence. So if I want a p of 0.9, and I'm looking for about the mean, I believe they use the word somewhere, within the range, about the mean, yeah, there it is. So that's telling me it's a t-value. So I'm going to look up the percentage, p, on this third chart here, all the way down to 0.9, and I get 1.645. So for problem 37, 1.645, that is my t-value. That's the number of standard deviations above and below the mean that will give me 90% of my data, or in this case, 90% chance that the true mean is within my range, okay? Same t-value works for both cases. It's kind of a cool thing. So if I want to find the interval, well, what I could do is take x bar, and I'm going to add and subtract t multiplied by my sigma sub x bar. All right. So if I take this t-value and multiply by a standard deviation, or in this case, my standard error of the mean, that will convert to units. If I add and subtract that units from the mean, it will give me my interval. So just to show that this works, this would be 1.8 plus or minus 1.645 times 0.0354, and I get 0.0582. And if I add that to 1.8, I get 1.858, which is what they got as my upper bound. If I subtract that from 1.8, 0.058. What did I say? 2? Yeah, good. And I get 1.7418 is my interval that has 90% likelihood of mu, the true mean, existing within it. So I'll just skip down to 39 for sake of time. So it says find the range about the sample mean that has a 1% level of confidence. So if the LOC is 1%, then that means my percentage is 0.99. Okay, and they typically are interested in always about the mean, and that's what it says here, about the sample mean. So that's a t-value. So I'll look up 0.99. Notice a lot of my chart actually here for the p-values is spent from 0.9 on. Almost half of my chart is all the 0.9s. So I look up 0.99. 2.576 is the number of standard deviations above and below. 2.576. All right, so to find the interval, I would just do 1.8 plus or minus 2.576 times my sigma sub x bar, which was the 0.035 or whatever I said, 354. Right? So 2.576 multiplied by 0.0354, I get 0.09, let's see, 1.8 plus or minus 0.0912 that I'm adding and subtracting to that. 1.8 plus that is going to be 1.8912 as my upper bound. My lower bound would be 1.8 minus 0.09119. And I get 1.7088. And yeah, that's what they got as well. I just got it within better margins, better accuracy. So that's the idea. That wasn't all the concepts on the test, but that was a handful of them. Thanks for hanging out. Have a great day. Good luck on your test, friends. Good luck. Or good skill. There's no luck involved. Good skill.